Okay, so hi everyone, this is Sean Mullery from Electronic Engineering at IT Sligo, and what I'm going to do in tonight's first lecture is I'm going to talk a little bit about what we call data wrangling, or we might call data munging, but it's basically this idea of how we deal with raw data and get it into a format that's going to be useful to us from either a data science or a machine learning point of view. So it's quite important for you yourselves, particularly in the assignment that I've just posted on Moodle, because a lot of that assignment is going to be about how you are going to format the data and clean up the data in order to make it useful for a machine learning task. So what is data wrangling? So raw data is usually not ready to directly use in a machine learning application. We normally have to do a little bit of cleaning up of it in order to make it useful, or putting it into the right format. So data wrangling can include just finding the right data. So finding the right data for our application can be included in this, whether it's that we go and find some database which might have the data that we're looking for, or it might be a situation where we try and infer it from maybe getting it from sensors, or infer it from other pieces of information that we can find in some database somewhere. We then have to kind of clean up the data, get rid of any data that's going to cause problems for us, and obviously make it so that the system is not going to crash, or is not going to know, it's not going to have a problem knowing what to do in situations where there's certain pieces of data that might be problematic. So maybe there's there's data that's outside of the range that we can deal with, or it's not in the right format for us to deal with, and so on. And lastly, then we might have to look at transforming the data to a more appropriate form. Okay, so it might be a situation whereby you're doing your feature scaling, putting it into the right thing, changing the data format of it, so changing it, the number format, maybe from an integer to a float, or it could be that you've got labels, and the labels say that it's label 1 or label 2, but you need that to be written as a number between 0 and 1. So from all those point of views, we've got to do a lot of changing about the data in order to do it. And sometimes, given, I'm not sure if I'm pronouncing it right, munging or munging was one term that I've seen it written as, but data wrangling seems to be the more common term. So the first thing we need to look at is the sort of formats that data might come in. Because we obviously want to have somewhat of a consistent sort of data format to be dealing with, so that we can then use them elsewhere. So good data formats should have the following sort of properties. They should be easy for computers to parse. So by parse, we mean a computer must be able to go through the data relatively easy to find out the piece of information that it's trying to get, so to read in the sort of piece of information that it's trying to get. Usually APIs will be available for that. The API just stands for Application Programmer Interface, if you haven't come across it before. So the idea is that data formats should normally have library functions that allow us to interact with that data in some way, shape or form. They should also be easy for people to read. That basically means that if we open it in its raw format, it should be somewhat easy for a human to be able to see what sort of data is in there. Oftentimes data formats might come in a fashion that, unless you have a computer program to read it, it doesn't make any sense. But we like data formats to be somewhat readable from a human point of view, so that we can just take a quick glance at it and make sure that it's got all the sort of piece of information that we would want. So typically human readable text encoded format, with quite obvious rows and columns of some description for us to be able to actually see the data as well. It should be widely used by other tools and systems. So it doesn't really make sense if we've got proprietary systems whereby we can't use that format elsewhere. So it's great if a format is somewhat common between a lot of different systems, because that means that it's going to be that much easier for us to run it on different systems and to be able to compare different systems as well. So the ability to mix and match and compare between different problems is very important. So therefore it's good if it's got some sort of common format. Now, it should also be efficient, but it is important to point out that when we talk about efficiency, this is sometimes mutually exclusive with some of the others that we've already mentioned. So for example, if it's easy for computers to parse, or it's easy for people to read, that might not be the most efficient way to put it. And we might also have problems with if we want to put it in an efficient way on one system, that might make it difficult to transport our port over to another system. So sometimes it's difficult to get the efficiency in there and also meet all the other criteria as well. So despite that fact that they might be mutually exclusive with some of the others, there are lots of compression methods that we can use. So for example, gzip is one method where you can zip or compress your data and then unzip it when it's ready to be used. So that can remove redundancies within the memory system that may come up with making it easy to read and easy to parse and so on. Keep in mind, memory is usually cheaper than developer time. And particularly when it comes to machine learning, we're normally doing machine learning on fairly powerful computer systems like machines that might have GPUs, or certainly on PCs and Macs and things like that, or we might be doing them in the cloud. But normally speaking, we're not doing machine learning on an embedded system. We may well deploy it to an embedded system later, whereby memory is expensive. And by expensive, I simply mean that if you have to duplicate it over millions of products, it's going to cost you a lot of money. But it's also might be expensive in terms of battery usage and things like that as well. So it's a different situation when it comes to embedded systems and we're deploying the system. Where we're learning, we normally have quite a bit of computing power available to us. So for embedded systems, the data set is usually not resident, as the data set is used for learning and in most cases not used for deployment. We are going to see an example in a later lecture where the data set is actually resident for part of the machine learning algorithm when it's in use. So that might not be, that's difficult to be efficient in that case. But in most cases, we're far more concerned with developer time and machine, the time it takes to develop to train the system than we are about memory. Memory is usually relatively cheap. So it is important to kind of keep that in mind from the efficiency point of view, that oftentimes it's the efficiency of programming is more important maybe than the efficiency of memory usage. And just check that you're all still with me there. Okay, that's great. Okay, so I think there's only a few in tonight so far, but we'll probably have a few more come along before we're too far into the lecture. Some important data formats then is the next. Okay, so Olivia's having a few connection issues. Are the rest of you having connection issues? I actually had a problem there when I was trying to. You did as well. Okay, so maybe that's. I actually, when I went to log on there, I also had a bit of a problem when I went to log on the separate computer as well. Yeah, actually, I think that's. I think I was trying it in Chrome and it wouldn't work as well. So maybe that's how an Explorer works. Okay, so I don't know. Was there some update maybe to the system? Okay. So listen, guys, if you've missed anything, you've probably only missed a few slides there, so you'll pick them up in the recording. I had the same Vin. It was when I tried to log on another machine. I set it up in the Adobe app and that seemed to work rather than just working in the web browser. So for the rest of you, that might work as well. If it asks you to download the app, maybe use the app instead. That might solve your problems. You're all in now anyway, so hopefully you'll pick up on what we're talking about. So we're going to look at some important data formats, and probably the most important of these is CSV, which is comma separated value is what it stands for. Now we say comma separated value because normally the comma is the most used delineator between different variables. So what will happen basically is you'll have like a number like 3, we'll maybe go on to there. 3.14 for example, and then you'll have a comma and then 2.18 and another comma and so on. It will separate them in this sort of fashion. However, there are other characters that you can use maybe that are less common than the comma, like let's say a semicolon, and you can use those to separate it as well. It depends though. You need to make sure that your program is aware that that's what you're doing, so that you take it in with the right thing. So a lot of library functions that deal with comma separated value programs, you can actually specify what is the character that's being used to delineate. And in the assignment that I'm giving you, the data set happens to use commas instead of, so for 3.14 it says 3,14, which is is used in, I think, other parts of continental Europe and maybe other parts of the world. I've changed that for you, but just be aware that that sort of thing can happen you very easily when you deal with comma separated values, that sometimes you might need to put a comma in somewhere else within the values that are in there, and how do you manage that? Okay, so each line is a separate record, and features are separated by commas in this case, usually readable by Excel, so you can normally just double click on it and open it in Excel or any other system. It can have subtle problems, such as I've mentioned there, with how to deal with the problem if your comma comes up elsewhere. XML then stands for Extensible Markup Language. It's structured but not tabular, so text, you kind of use like those angle brackets that you see, angle brackets and something to kind of say what's in there, rather than, you know, a little bit like you'd see in HTML and things like that. It's good for including markups in a document, but it's not necessarily that easy then to see in a tabular format, which can be useful with the CSV thing. I'm talking about just when you open it to look at it in its raw format here. So SQL database, which is not strictly a data format, but it is a kind of a very important system for being able to get information out of databases. It stands for Structured Query Language. You may also hear people call this SQL, when they're basically making a phonetic version out of SQL, but it is meant to be called SQL rather than SQL. It's a little bit clunky, but it is very powerful. It's a very powerful query language. Most people have had exposure to it at some point or other, and there's lots of different libraries or APIs for different languages to allow you to interrogate a database from any programming language using SQL. As I say, it's not strictly a data format, but because it can export as other data formats, but it's nonetheless an important data storage system and retrieval system. So from that point of view, we wanted to mention it here. Another one then is JSON, which stands for JavaScript Object Notation. You might assume then that it only works with JavaScript, but actually that's not the case. It works in Python and a lot of other object-oriented languages as well. It's basically used for object-oriented languages, and it allows for transmitting of data objects between programs. So natural communication of the state of data structures and variables is very useful for that. Basically, a list of attribute value pairs is what you get with this. So you've got an attribute saying what it is and then the value for that attribute. It is human readable in that if you open it up in a raw format, it is somewhat readable, but it's a little bit cluttered. So you normally need a little bit of expertise with it before you're able to kind of spot what's in there. Now, there's a term I'm sure many of you have heard, which is garbage in and garbage out. Or garbage in means garbage out, effectively. So if you put data in, it doesn't matter how good your algorithm is, you're not going to get a good result. Now, to some extent, this is something that you find with different types of engineers and computer scientists in terms of separating what they're doing with what somebody else is doing. And what they're basically saying is that, look, my algorithm is fine, it's your data that's garbage. From our point of view, you know, as machine learning practitioners, it's important to get away from the idea of just being an algorithm developer. You do need to also understand that actually the quality of your data is just as important as the learning algorithm. And if your data is bad, what you're going to get out of it is going to be bad as well. And that is your responsibility to actually look at the data and make sure that it isn't garbage. So if we use wrong data, we will not achieve a correct result. Often we have to clean the data, and just be wary of this word clean, because it can have a negative connotation as if we're doing something fraudulent, and I'll address that a little bit as we go through. But the point is that we often have to change our data into a format that's actually usable by our machine learning system. And rather than that being something fraudulent, that's something that we just have to do in order to make the system work. It is very, very important when we do this that we're very clear with whoever's looking at our experiment or whoever's reading it, that we're clear about the methodology that we went about in order to do that, so that they could then reproduce it. And it's also very important that we keep a hold of our raw data so that people understand, here's the raw data, here's what we did to it, here's what we ended up with, so that somebody can reproduce that and then determine, if there's something wrong with our methodology, then somebody is free to say, I think there's a problem with this, as long as we're very clear with them what we've done. But if we're not, then it's very difficult for somebody to tell whether we've just made a mistake or whether we're deliberately trying to mislead people. So we need to be careful here that we are not skewing or biasing the data by doing this cleaning, as this could lead to, could be misleading, and it could indeed be research misconduct, and that can be very, very serious because it can have real world effects beyond just a researcher being led astray. So we also need to be sure that we do not introduce problems by doing so. So in particular, that we don't accidentally produce erroneous data by this cleaning operation that we do. So this guy, Stephen Skiena, I hope I'm pronouncing his name correctly. He's most of this lecture came from a textbook that he's written, and it's all about data science. And he separates out this idea of errors versus artifacts. He has a separate definition for them. So he basically says that data errors are, he views them as unrecoverable problems with the data. So for example, in a data acquisition system, if a sensor fails and we're no longer getting data from that sensor, that would be a data error, because there's no way of us actually getting that data back. Okay. On the other hand, what he defines data artifacts as is a problem that can be recovered if they are identified and the original data is still exists. So if we introduce something into it by processing that we're doing, well, if we still have the original raw data, we can go back and redo that properly and get that. But if we don't have the original raw data and we do this, we can very easily introduce artifacts into the system which lead us astray and give an incorrect output. Now, simply having the raw data does not mean that we will necessarily spot that we've done this. So this is a little bit like bugs in any software system. We have to be very careful to try and rigorously check what it is that we're doing, so that we can spot that we've done this. And there are various ways of trying to do that, but a lot of it comes down to just being very diligent about what you do. The takeaway here is twofold. Never overwrite your original raw data, firstly. Always try and keep a copy of that so that you can always go back to it. In fact, in many cases, people will not trust you unless you have that original raw data available and they can see the entire pipeline. That's why those Python notebooks that you've seen and the other forms of notebooks that you have where you can write computer code and have notes written in between, they've become extremely popular because it allows somebody to look at your work and see every step of the way and redo that step, and also modify it then to see, well, okay, what would happen if I did this, that, or the other. So that can be very useful to be able to write your programs as a notebook. The second thing you should do is check rigorously if you've introduced an artifact into the data. So in the same way as, most of you who work in a large company where you develop software, you're going to go through an entire pipeline of software engineering, and you're going to have people checking your code and checking it for bugs and different testing going on there. In the same sort of way, you've got to do the same sort of things with your data. Always checking your data to see, have you introduced something here that's going to do damage? And oftentimes that can be very difficult to do. So how do we go about maybe finding some of these errors or artifacts? You start with what you expect the data to look like. So one of the things about data and about probability and statistics, and some of you have already done a full module on probability and statistics, and others will be doing it next semester. But there's a thing about the difference between probability and statistics. And statistics is where, we go and we gather some data, and that's statistics. And when we analyze that data, what we're really trying to do is we're trying to find out something about the underlying process that created that data. So once we know something about the underlying process or the model that created that data, we can then make, probability predictions based on that model or that underlying process. So the reality, you might think of it that we always go and we gather data and then we try and find out something about the underlying model, but sometimes we might have some prior knowledge of the underlying model, and from that be able to look at the data and see, does it match or are there anomalies there? So in many cases what happens is we have an underlying idea of what the thing should look like, so what we expect the data to look like. We then compare that with enough statistics to see is there anything different there or not? Now, when we do that comparison, and if there is something different, we need to be able to explain why is it different. Okay? So we compare this with what we see versus what we expect. If they're different, can we explain why they're different? So remember that one of the primary reasons for working with data in the first place is to find these differences, find things we weren't expecting. If we only found things we were expecting, then data science wouldn't be particularly useful to us because it wouldn't teach us anything about what we're looking at. So we are always looking for the unexpected, and therefore if we just saw things that looked like what we expected, it would be no good. That said, when you first find something that you don't expect, your first assumption always should be, I've introduced an error, I've introduced an artifact, or there's an error in the data. Okay, there's some problem that has caused this. That should be your first assumption. And it's only when you've ruled all of those out that you can then hope to be able to say, I found something of interest here, and now I'm going to try and track down why I'm seeing something different than I would have expected to see. So again, for any of you who've done any programming over the years, certainly I find with novice programmers, you know, with our level 6s, when they come in and they start programming, their first assumption when they see a mistake is there something wrong with the compiler? Now, there are sometimes problems or bugs with a compiler, but it's actually very, very rare. It's far more likely that a novice programmer has made a mistake than there being something wrong with the compiler. That doesn't mean that there's definitely nothing wrong with the compiler. It's just that you've got to be able to rule out that you've made a mistake first. So very much the same with data. And for a lot of you, you're dealing with data for the first time here. You need to be aware that when you spot an anomaly, it's likely you've caused the anomaly, or you've not taken account of something that has caused the anomaly, as opposed to that you've actually gone and found something original. So always assume those things first, and it's only when you can rule all of those out definitively that you can be sure that you've found something new, and then try and track down, okay, what is it that caused that? So that's usually our best mechanism for finding these things. The next thing we look at is data compatibility, which is, you know, if we've got data that we want to put together coming from different systems, you know, how do we go about that, and what are some of the problems associated with it? So I have an example here of where some scientists tried to put together some different types of data in order to try and find out something that was obviously vitally important from a planetary point of view. So what they were doing here was they were trying to determine, back in the late 1990s, whether the climate was warming in an anomalous way. In other words, in a way that it hadn't done previously. Okay. Now, the difficulty that they faced is that they had good records on temperature, on global temperatures, that go back to about 1850. And this is generally when we refer to the idea of when records began. Okay, because people started recording these things in a significant way. And that's the section that we can see here in red. Okay, so this section here that we can see in red, that's the section that they had data from. The problem is that they were really trying to determine whether the climate was warming in an unusual manner since the Industrial Revolution. And of course, the Industrial Revolution more or less started just a little bit before, around about the time that records began. And you can see the problem there. If we don't have records going back before that, how are we going to deal with this issue? Now, basically what they did in this particular case was they found cycles within the data that were related to the El Nino effect you might have heard of, or there's another effect that happens somewhere in the North Atlantic as well, and they found that there were certain fluctuations that seemed to happen with a period. And what they then went back and looked at things like tree rings and carbon dating and carbon within samples and so on in the ice cores, lots of these different ideas, and try to see, could they use that as a proxy to determine what the temperature might have been during the times when they didn't have data. And what they found when they went to do that was that they found those same cycles that they found in the data that they had good records for. And that gave them quite a good indication that they had good proxies for that data. So from that they then were able to create temperature data for the climate that went right the way back to 1000 AD. Now you can see this is the dark blue signal that they have there. And you can see that obviously at different points in time, such as there, you can see that they're a little bit more unsure of this data back at that stage than they were of this, and certainly they're much less unsure here because they have very good data for that. So they've included that within their models to say how unsure they are. And what they then were able to kind of say was, okay, well look, this is the worst case scenario going along here, and as we can see, we've had a rate of warming that's just way out of kilter with everything that we've ever seen before. Okay, and of course, as you all know, once we saw this back in about 1999, 2000, we immediately solved the climate crisis, and we all lived happily ever after in a low carbon economy. Well, it's not really what happened, of course. What happened is that, well, we're still trying to deal with the problem today. But the second thing is, you may be quite aware of this, that there was a lot of controversy over this particular graph here. And the controversy over it is, how did they go and match up the blue graph with the red graph? And did they do it in an appropriate manner? And it's not really for us to comment on it without going into a lot of detail. But as you can see there, there's a green line there as well, where somebody has later gone back and tried to use their own methodologies, updated 10 or 15 years later, in order to try and determine, are they seeing the same sort of things? And they did indeed see the same sort of things. So when it comes to this sort of thing where you're trying to put data together, you've got to be very careful about how you do it and whether you're doing the right thing, because in many cases it can be something vitally important. And if people don't trust your methodology, they also don't trust the results, and that can often make things much more difficult. With any of these things, with something that you do, when you do scientific work, so we've scientific work, we vary over a scale with regard to totally wrong to totally right. And most scientists will tell you that they're never totally right. They're just getting slightly less wrong as they go. Okay? So you're somewhere on this scale here. And this is where your methodology is very important, because if somebody finds later on that you were more on this end of the scale, more towards the wrong end of the scale, there's then a determination of whether you were intentionally wrong in order to try and mislead people, or whether you were accidentally wrong. And that's where people obviously get into trouble for being fraudulent and so on. So it does seem that the analysis by other scientists of this particular graph was that they did pretty well with regard to what they did. Their methodology was pretty sound. It wasn't completely right, but it was as good as they knew at the time. Others have gone back and maybe got it slightly more correct, but that they were broadly correct, and that there's certainly, if they're broadly correct, then there's not really a fraudulence to look at in that particular case. Okay, so that's the idea of putting data together, and you have the same problem if you're trying to get data from different sort of places. And I think you even have, some of you have a module called sensor fusion, where you're trying to put together different pieces of information and trying to see, well, how are they going to work together? So when it comes to this, you need to look out for the standard sort of things that we're likely to get wrong. So incompatible units, for example, imperial versus metric. And NASA indeed got this wrong. They lost a Mars climate orbiter due to this back in 1999, where two different systems, one was working on imperial, the other working on metric, and they didn't realize that they were working on different systems until the orbiter was already heading for Mars and it headed to the wrong place. Okay, so you can see how that sort of thing can happen. Watch out for features that might not be time invariant. And by time invariant, I mean that it doesn't matter when they happen, that they should be the same. So, for example, if you compare wages from different periods without taking inflation into account, you can see how you're not comparing like with like. So wages are really something that's relative, rather than relative to the time that they're in, as opposed to being completely invariant over those times. This also accounts for sudden changes that might occur. So, for example, inflation tends to happen slowly over time. But let's say you were comparing fuel prices in Ireland in October and November. So you can see there that obviously, if you may not be familiar with the Irish taxation system, but basically the budget happens in October, and oftentimes they will actually make a change to the taxation on fuel that takes account, that literally is put on the next day. So if you were just looking at data, or you might be looking at data that was that relied on this sort of information, relied on this, had a correlation with it, such as household disposable income. Well, household disposable income is going to change if a further taxation is put on fuel, because they're going to have less disposable income to use. And that might have, it mightn't take effect over a single week. It might take a few months before a household realizes that they don't have as much household income to play with, and so on. And if you look at that data and you don't take into account those sudden changes, then once again you've got a compatibility problem. So you might often have to correct for this sort of thing, and it would be vitally important that you write that into your methodology. You might have numerical representation problems, so floats, integers, etc., and particularly overflow or precision errors can cause major issues. Indeed, there was an Ariane 5 rocket that exploded back in 1996, just after liftoff, I think about 40 seconds after liftoff, and it was simply because somewhere in an embedded system there was a non-successful conversion from 64-bit float to a 16-bit int, and it just didn't work properly, and it caused that rocket to explode. So that's obviously a very serious effect of these things. But if you're dealing with autonomous vehicles, you are also dealing with things that can cause injury. So it's important to be aware that data formats and so on can all data representation problems can all cause issues with that. Another problem that you might have, particularly in machine learning, is that you've got a whole data set there, but you find that for some of the features there are missing values. Okay, this could be that you've done something like a survey and not everybody has filled in all of the values. So what do you do in that situation when that occurs? Now, as it happens in the assignment that I've given you, this occurs because some of the sensors, not so much the sensors, but some of the values that are determined from the sensors, such as your average speed that the vehicle is moving at, it needs a certain amount of data before it calculates an average value. So I think it needs 60 samples before it calculates a single average value. So for that reason, you can see the problem that you're going to have there. You're going to have missing values. And what do you do with those missing values when that occurs? Okay. So the simplest thing to do is to just remove all the records that don't have complete data. And that's what I've done in your case. I've already done that for you. I've removed I think I've done them all, but you're going to have to check them to make sure that there's nowhere else where there's missing values there. So I've basically removed the samples that didn't have those. Now, of course, the other thing that we understand from that is that data set that I've given you, you're going to treat that as if each sample is completely independent of the other samples. That's not actually the case, because of course it's taken over time. So we're just going to treat it like that as an assumption, but of course we do need to be aware that could cause us problems down the line. So the simplest thing, as I say, is to remove all the records that don't have complete data. At least everything you are left with is correct in this particular case. If it leaves enough data, then it's probably the best method to use. And there's actually only a small number of them that we're taking out, so that's fine in our case. It assumes, though, that values are missing randomly rather than for a systematic reason. Now, we know in the example I've just given you that it is actually for a systematic reason that they're missing. So therefore, it's not as good a reason for just removing them as we would get from if they were randomly missing. If the reason is systematic, then your model can end up being biased, and I think it's likely that the fact that our samples in our assignment are linked by time, I think that is liable to lead towards a bias. We're just going to have to be aware of that and try and deal with it within that. The other thing you can do with missing values is use some heuristic input. So I don't know whether you're familiar with this term heuristic, but heuristic is like a rule of thumb. In other words, rules that, like vague rules that we do under certain circumstances, a bit like an educated guess. And so you might say, well, within certain circumstances, this is what we'll put in for this particular value. Your assumptions will have an effect and could bias the result as well. And as well as that, if you are filling in values like this, it would be important to write that into your methodology. To say, or to write it into your method to say, this is how I'm dealing with these missing values. This is the heuristic that I dealt with, so that somebody else can go back to your raw data, then look at the data that got created by you to fill in those blanks, so that they can then say whether they think that's a good methodology or not, so they can argue the case. The other thing you can do is you can take the average of that feature and put that in for the gaps. Now, the good part about this is that it doesn't bias your overall data set. Because if everything goes in as the mean value for those cases, then your overall mean is not biased in one direction or another. So this leaves the mean of that feature unchanged by putting in the mean value, putting in the average value in each case. So no bias change. Again, this may not be appropriate with a systematic reason for missing values. So one example that Stephen Skiena gives in his book is that you might be looking at details of people within a population, and there might be the age that they died at, okay, or the date that they died at. And in those circumstances, you're going to have a lot of missing values for people who are still alive. And it's not appropriate to put in a mean value for a date that people are dying, because that suggests that some people may even die before they're born. So in certain circumstances, it's just not appropriate to put in a mean value, but in many cases, it can be fine. You can do something like input by nearest neighbour. Now, in the next lecture that I'm going to do with you tonight is on nearest neighbour, so I'll explain to you a little bit more about that later this evening. But this can be a good method if the problem is caused by a systematic problem. You need to have a reliable way of calculating the distance in the space to the nearest neighbour, and that can be problematic. But if you do know a way of doing that, then this can be a good method. You can input by interpolation. In other words, if you have two values and you've two data points that and you know that those data points are some distance from each other, you can try and find within that space, however many features are in that space, you can try and find a point in between by interpolation. Normally by a linear interpolation. So what you're effectively doing is you're using linear regression between two data points in order to try and find a straight line between them to pick the point in the missing space. In effect, this is using linear regression. It depends on the way the data is collected, but be wary of this in general for machine learning. And the reason is that what you're effectively doing is you're using one machine learning mechanism, like linear regression, to try and build up the data that's then going to be used to train another machine learning algorithm. So there are certain problems with this. It might be useful in terms of just displaying data for other data science, but for machine learning, it's maybe not the better method to use. It can also lead to some outliers. So it might be that there's something missing in the data off the end, and it can be that if you continue on that straight line, what you're effectively doing is extrapolating rather than interpolating. You could use just a random value input, and this may seem a little bit crazy, but actually it's a very useful method indeed. If you run the training, the idea here is that you basically run the you put in random values with a certain variance that fits in with the data set. And so if you run the training multiple times with different random values, you should find that by filling in those inputs, filling in those blanks with random data should not have a major effect on the model if you fill them in differently each time. If we're seeing that is actually fairly widely varying the model, then we know that that we're not actually robust to that problem, and that actually it's not learning much from the proper data that we have there. So it's quite a good system from that if you run it a number of times and see what comes up. One final point on this, and it's something that people who are not statisticians, and maybe some of them who are corrupt statisticians want to do, is filling in blanks with the value that you'd really like to be in there to suit your hypothesis. There's no other word for that other than fraudulent. Okay, so if you're filling in blanks with your preferred value rather than some average value or something else, then you're not trying to learn something new. You're trying to prove some point to somebody, and that's just fraudulent when it comes to data science. So just don't do that. That's why that's written in bold letters. You're not doing science at that point if that's what you're doing. Now, another problem that we can face, and it is a problem you're going to see with the data set that I've given you, and it's a particular problem in medical circumstances or in the autonomous vehicle space as well. And it's this: we don't have enough samples of classes that are unusual. Okay, so consider the following problem. We have a data set of features of healthy and sick individuals. As the condition is rare, and rare could be a lot more rare than I'm giving here, let's assume that of the samples that we've taken, in other words, people have come into hospital for some reason or other, so that you might have a higher percentage than normal, but 2% of the samples have the condition, and 98% of the samples are healthy. i.e. don't have the condition. Now, if I build a model, let's say I build a really, really simplistic model, even more simplistic than linear regression or logistic regression or anything like that. I build a model that simply responds, the subject is healthy. No matter what sample you give me, I say the subject is healthy. Do any of you want to guess how often will I be right? So what percentage accuracy will I have if I just always say that the person is healthy? Do you want to take a guess at that? Yeah, so Finn is saying 50%. Anybody want to? If you don't type, I'm going to assume you're agreeing with Finn. Okay, Olivia's saying 98%. Yeah, exactly. So 98% is correct here. Now, in Vin's case, if I was flipping a coin here and it was a 50-50 chance, and I always say it's going to be heads, I will be right 50% of the time. That's certainly true. And that's often happens between two options. Random chance will give you this. But because of the samples that I have, if the population is 98% healthy, and I always just answer healthy individual here, I'll still be right 98% of the time. And that sounds really good, that I'm right 98% of the time. Unfortunately, it's the 2% of the time that I'm wrong are the people who are ill. And you can see a significant problem with that. So this is one of the problems with unbalanced training classes. That if our algorithm is not getting above 98%, we know we're in bother. A second example, question I have for you here. If I train a model in some way, and on the training data that I have, which as we say is 98% one class and only 2% the other class, and I get 83% accuracy, what does this mean? And what this effectively means, well, it could mean a number of things, right? It could be that I get 83% of the 98% correct, in which case a lot of the time, so some 17% of the time, I'm giving a false positive. I'm saying that the person is sick when they're not, okay? Or we could have the example where I'm getting all 2% of the sick people correct, but the other, whatever's left, 15%, I'm getting those as false positives and saying they're sick when they're not. Okay? Which is better? Well, you know, you can trade off these false positives, false negatives, and all these sort of things. But in truth, you know, if it's in medical circumstances, you don't want to tell people they're sick when they're not. It can cause a huge amount of pain for those people. But at the same time, you don't want to get the when somebody is sick, you don't want to get that wrong either. So there's a balance to be struck there. Our main thing from our point of view is that if we're training something with unbalanced classes, we have a problem to deal with. Okay, because of this, that it's going to lead to a lot of false. So if we want to balance an unbalanced data set, how do we go about it? So we round up more elements of the rare class would be the first thing if we can do it. And I mentioned that this is something that Tesla does. They have systems in their cars that if something unusual happens, in other words, that they make a prediction of what they should do next and that's not what happens, or it causes some problem, let's say that the person takes over driving because they didn't want the car to do that, then they record that and that gets sent back to a central server once they're connected up to the internet. At that point, what they then do is they look for more examples of that class. So they send back out a condition to the fleet to say, if you see this unusual thing happen, will you report it? Okay, so report it back. So they can, by this method, they can actually get elements of the rare class more often. The other thing you can do in autonomous vehicles is, of course, you can do simulations and try and simulate the rare classes. The problem is it's sometimes hard to know about the rare classes in order to have them in the simulation. Okay, so that's one thing you can do, but it's not always feasible. It's not always feasible to find more people who are ill. And Stephen Skiena in his book gives the example of trying to find terrorists amongst the data. Well, there's relatively few of those, thankfully, and therefore it can be harder to find the actual samples of that rare class. The other thing you can try and do is you can force a balance by discarding members of the more abundant class. Okay, so you can just get rid of a lot of elements so that you bring it down to things. So, for example, in our case, what we might do is we might have 2% of people who are in the class that have the condition. And what we do is we get rid of 96 out of the 98% of the class that don't have the condition in order to balance up the set. This is justified if you have enough instances of the smaller class that when you have double that size that you have enough to build a reasonable classifier. If you don't, this is probably not a solution. The other thing you can do is you can replicate elements of the smaller class. So we can replicate elements where somebody has the condition in this particular case by doubling or tripling or quadrupling or whatever we do, maybe making 10 times as many of them. If we just make identical elements, then we risk overfitting in this particular case, because as a model that gets one wrong now gets many wrong, as you can see, because for every one that it gets wrong, if you've got 10 copies of that, it's going to get 10 of them wrong. So it's like making each smaller class element many times as important as it was. If sorry, I have a mistake there in the text. Moving that sample from one side to the other of a boundary, a decision boundary, has a large effect. If we had a perturbation which is random, so in other words, we make copies, but we make a certain amount of randomness around it, and that randomness has a variance that's consistent with the general population of the samples, then that can actually work a little bit better from that point of view. And in terms of image processing, when we get there, we do this by what we call data augmentation. So we make we take images that we're going to go into our deep learning system, and we rotate them slightly, or we flip them if that's appropriate, and there's different or we add maybe some noise to them in order to make up more data than we originally had. The other thing we can do is we can weigh the rare class more heavily than the abundant class in our loss function. So this has similar problems. So our loss function is now a little bit different, but it treats the rare class as being more significant than the abundant class. It has the exact same problems though of overfitting, where if you move one side or the other of that boundary, it can cause a massive effect. And what it'll do is it'll realize that if it changes its model to hit some of those some of the examples that we already have, then rather than trying to be more generally good, then we run into the same sort of problems again. So what can happen is that when we're trying to balance things, we can also introduce a bit of a bias into the system by doing so, not necessarily intentionally, but just by virtue of what we're doing. So while these are the best methods that we have, they still face a problem. All these ideas bias the model to think that rare events happen much more often in general. Now that may or may not be a problem, but if you think about the example of an autonomous vehicle, we find rare events, where somebody suddenly cuts into your lane, which normally wouldn't happen, or maybe somebody runs a red light, which normally shouldn't happen. Okay, but because they rarely happen, we produce much more of them so that our system learns what to do in that particular case. That may seem fine, but it now leads to a vehicle that thinks that that's going to happen quite regularly. Okay, so it automatically falters when it has a green light, despite the fact that it shouldn't. It automatically assumes that cars in the other lane are about to jump out in front of it when they're not. What happens in that case? Well, we end up with effectively a very nervous car. A car that isn't sure what to do next, or gives the occupants a really uncomfortable journey because it's constantly jittery and it's trying to jump in different directions because it thinks the other cars are going to do something more dangerous. Despite the fact that they may not be likely to do so. So that is one of the problems with giving the overall sense of what we're going to do. We change the statistics of the real world because we want to give more samples that have the particular problem. Okay, so the reason I wanted to cover this lecture, I went back and put this lecture earlier, was because I've given you the assignment that I want you to do, and I've put you into groups there as well. I'll send you out a bit more detail on that this evening or tomorrow as to what groups you're in, although you'll probably figure it out from the forums on Moodle. But one of the things that I want you to do is to actually go through and solve some of these problems before you then run it, because that's an important part of becoming a machine learning practitioner. Okay, so what I'm going to do is I'm just going to end this recording here, and then I'm going to start the second lecture, which should be a little bit shorter, and we'll hopefully be finished within about 20 to 30 minutes.